her work, I think, immediately stood out as highly, highly technical, really detailed. And then her presentations, of course, on like what made it work, how they were done at both a software and hardware level, just were fascinating. She had a ton of excitement and energy, was deeply expert, and then she spent the last decade doing even more interesting stuff. So at Project Zero, obviously you're all familiar. I don't even think, most keynotes don't need introduction, and it is cliche to say, but it's very true. She has been an expert in the field for many years. I am really excited and happy that we've been able to get her here to be our very first keynote to talk about just her process for reverse engineering, for approaching an attack surface to target space. And we're going to get to see kind of what the process looks like, the things that work, the things that don't. And I think it's going to be really useful whether you're doing reverse engineering for vulnerability research or you're just even general kind of doing any problem solving. So with that, please give a big round of applause for Natalie.
Inviting me, Jordan. And I have to admit, I was a little bit alarmed by the promise of thoughtful keynotes. Now, I really hope I put enough thoughts into this one. And thanks so much, all of you, for coming to listen. Today, I'm going to talk about how to find fully remote bugs with reverse engineering. I'm Natalie Silvanovich, and I'm a team lead on Project Zero at Google. And I've always been a bit of a messaging enthusiast. I've always been fascinated by zero-click bugs. It just seems like magic to me that you can find a bug in a messaging client, and send a payload and compromise that client without the user touching their device at all and without network proximity. So I've spent quite a few years researching this topic. And in the past, I've reported a lot of zero-click bugs in iMessage, Facebook Messenger, Signal, and a lot of other messaging clients. But today I'm going to talk about my recent review of Google Messages. And Google Messages is the default Android messaging client. And it used to be on just some Android devices, but that started expanding. Some OEMs had their own messaging client, but they've moved to Google Messages, and now it's at about 5 billion downloads. What's also interesting about it is that it recently implemented RCS. And RCS is the new SMS protocol. It's the replacement for SMS. And this meant that there was basically a rewrite of this app. Tons and tons of code was added. So I was kind of curious, could I find any zero-click bugs in this new protocol? So this got me down to the central question that I always start with during these reviews. How do you determine the attack surface of a brand new app? And I did a few things. To start off, I always use it. And of course, I'll set up 2 devices, I'll send messages back and forth, I'll try and figure out all the features. But, I also like to actually sign in and actually use it for a few days. And you would be amazed by what you figure out. For example, got this video. This is just receiving a lot of messages that say, I love you. And look at what shows up. This selfie button, encouraging you to take only the most highly appropriate selfies. And I looked into this, and it turns out there's actually a tiny little classifier in there that is measuring the selfiness of all your messages, and if they're selfie enough, it'll spawn that button. And, I gotta say I don't have a clear plan here, of how this could be an attack surface. But, maybe there's a bug in this classifier if you send the right message. Or, maybe it loads an encoder that would be useful during an exploit. I don't really know. But this is the sort of thing that once you start actually using an app, you'll notice this attack surface. And I don't think I would have ever figured this out if I hadn't sent messages saying I love you back and forth for an hour. So the next step is I'll look at the code, and if I have it, and the APK. And I've actually seen the code of this app before. Back when I was on the Android team at Google, I was actually the security reviewer of the very first version of this app, which means I'm really old. But in this case, I mostly focused on reverse engineering. So I extracted the APK using APK tool to start. And there's pros and cons of this. To use Signal as an example, because it's open source, this is the Signal code base. And by looking at this, you can figure out quite a bit about the attack surface. And what I think the best thing about code is you can really learn a lot about developer intent. You can figure out components, you can look at the commit messages, you can look at class names. And that's really beneficial in terms of trying to figure out what the feature set is. But there's also a lot of things that you might not notice if you just look at the code. For example, here's the binary libraries in the APK of Signal. And there's some things you'd expect, like libsignal, but then there's things you might not, like libmobilecoin. What's that? And then there's also ringrtc, which is what they use to set up phone calls. And I actually found a bug in an old version of that a long time ago. So this is especially important in Android apps, too. So if you look at how Gradle builds them, there's lots of dependencies, and these dependencies can chain for quite a long time. And Signal has actually cleaned this up quite a bit, but 2 years ago, you'd look into the first Gradle, and it would be oh, my shiny corner, and then it would be Bob's shiny corner and Fred's shiny corner, and if you went all the way down the chain, there would be quite a few third-party components included. And you can do that, but it's also sometimes a lot easier if you look at the small-e or the decompiled Java, and all of this stuff will just be compiled in, so you don't have to worry about what is that component that is included, or is that code being used? You can usually tell right away. So I opened up the Google Messages APK, and I was immediately surprised. So this is 24 native libraries. That is a super large number for a messaging app. So this kind of started giving me an idea of what the functionality of it might be and how I might start looking at it. So the third thing I do, and this is especially good on Android, is I'll start looking at the logs. Android has a really large amount of logging, and for this sort of thing, it's pretty excellent. And part of the problem with Android, and especially with kind of the special Google apps that are written by Google, is that a lot of the attack surface will be outside of the app. So there'll be media services it uses. I also eventually found a classifier service it uses. And that, if you just look at the app, if you just look at the code of the app, you might not notice that. But if you turn on logcat and send an incoming message, you'll notice that right away. And as a little tip, Pixel devices tend to log a bit more. If you can, try your app on a Pixel device, and sometimes you'll get extra logging. You can also use coverage tools. If you have code, nothing's better than ASAN coverage. But on Project Zero, we also use TinyInts, which was written by a Project Zero member, Yvonne Fratrick, for coverage, and you can use that without code. I also sometimes like using Frida. I'll show how to do this later, but you can use Frida to dump basically every native method that's being called as it's being called. And you can do some nice logging, so then as there's an incoming message, figure out what's happening. And of course, this is it's an imperfect way to do things, because of course, if you send it a message, it'll show you what it's doing. But there might be this secret message type that never gets sent, and that is often where a lot of the bugs are, things that are only sent in some circumstances. But this can be a start. If you look at how normal messages are handled, that's where you can start to notice, oh, there's a switch statement with 5 things, and they only send 2 of them, and what do the other things do? And to give an example of this is getting an incoming message. It's the logcat. And if you zoom in here, you can see there's another little text classifier. And this is finding links, and this is the thing that makes the links turn blue in the message. So finally, the last thing I do is read the spec. And I would say specs vary. Sometimes you'll read a spec and you'll see a feature and be like, oh no, that looks terrible. There's just no way that worked right, especially if it's very complicated, if people are clearly not using it. I would say the RCS specification was not so much like that. But there were some interesting things. One of the most interesting parts of the spec, in my opinion, is they have these user stories with these very contrived user stories. As a user, I want one single entry point to voice calling independent of the enabling voice service. Yeah, I was in the Apple store the other day and I heard a guy ask for that. But some of these can teach you interesting things. For example, if this is true, maybe they need handover. Maybe they need ways to switch between networks. So sometimes if you think these out, you'll learn interesting things. And to give another example, it says every file format that RCS should support. And for example, it supports PDF. And the other bad part about specs is that they're not always accurate, and just, spoiler alert, this is also wrong. But sometimes you can find things out, like maybe you wouldn't have thought about looking at panoramic photos if you didn't look at the spec. So once I'd done all of these things, what did I do next? Determine and prioritize the attack surface. Not. I ran and looked at all the shiny things. Those classifiers were just so exciting, I could not resist, so I just had to look at them right away. And I was amazed by how many of them were. Almost half of the libraries in this messaging app was classifiers now. So I was really curious about them. They were native libraries, and some of them were split out into other system services. And back to why looking at these libraries is a good idea. So something that's true about most Android apps, especially the big ones, Facebook Messenger does this a lot too, is that there's a lot of different Android devices, and there's lots of different versions, and things don't always work. So a lot of the bigger apps, they'll embed libraries in the app as kind of a backup. So most of the time, they'll use the system service, they'll use the media service, that sort of thing. But then they'll have, for example, the backup media libraries, and this is what all this was. So when I looked at this running on a typical device, a lot of these libraries weren't actually used, but they were indicative of the services that the app used. So yeah, I looked at these. A lot of them were in system services. A lot of them were in the fully remote path. And I just thought, memory corruption in one of these classifiers would just be so cool. So I went and looked at this a bit more. And this is generally how one of these classifiers work. They don't have very many entry points. They typically have 3 functions. And the first one is load model. So there is a model on the file system, and it will load them. And that comes from Google. The user can't change that. And then there will be the second function, which kind of does the thing that the classifier does. And in this case, this is the detect language classifier. It takes a string in, and it detects what language that string is in. So this is the thing that this classifier does. And then finally, there's just a function that makes it stop. And using Frida, I was able to figure out when these classifiers get called. And this is at the top. This command is a little trick I like to figure out attack surface a bit. And I limited it to things in this com.google.chat class, which is related to classifiers. But if you want to figure out all the natives that get called when you get an incoming message, you can just do Java star, and it'll print out all of them. And you can see from this, there were kind of 6 classifier functions in this one process, and then it will spit out which one gets called when you send a message, and in this case, it was just this one, detect language. Another thing to be aware of is most of these messaging apps are also multi-process these days, so I had to do this on every process, but slowly I figured out which ones were in the remote path. So using Frida a little bit more, I wrote a little script that did input and output. This just kind of shows how this classifier works. So the text input is like a string of maybe the last 4 messages you did. And then every time you get a message, it moves the window. And you can see in the beginning, with all the I love you, it's in English. And then as I slowly move to je t'aime in French, it will output that this is a French message. So this is like what this specific classifier does. So I started off with code review. I reviewed this detect language function in IDA. And there were a few others. There's annotators, actions, language transcription, sensitive content, et cetera. And most of these were fully remote, so I looked at all of them. And to start off, the code was quite opaque. There's lots of things you look at, and it's really clear what they're doing. These were like, math on top of math on top of math. But what was also, unfortunate from a bug finding perspective and good from a software quality perspective was that the parsing was pretty consistent. I was hoping I'd go in and, find, 5 different parsing libraries and every one of these that does different things, but this turned out not to be the case. Standard libraries like, standard string were used, standard Unicode library, that sort of thing, and they all basically did their initial parsing the same way. So not very much code there. And I would say overall, just not as much reachable code as I expected. When I opened up these libraries, they were just huge, but it turned out that most of that code was used to parse the model when it was loaded. And the thing that the actual message touched, which is the thing that the attacker can control, was quite a bit smaller. So yeah, the code wasn't very huge. And I also learned that it was very model dependent. Like, there were lots of things where, with the right model, that might theoretically go out of bounds, but there was kind of no practical way to get to that model, so it wasn't really a bug. So very sadly, I did not find any bugs in these classifiers with code review. So I thought, what if I fuzz them? So I built a little fuzzer for this. And I did this by building AOSP, and you can actually build it on Linux with a host JVM and run little command line applications on your host. And I did this, and I made it call into the JNI. And yeah, this was the worst fuzzer ever. It was a bad idea. It did not work. I would generally recommend not doing this. It was super slow. Coverage didn't work right because of all the JNI calls. And also, the model needed to be loaded every time, or else it might learn something, and then your bugs weren't reproducible. So yeah, this was very slow fuzzing. I maybe just shouldn't have done this in the first place. And unsurprisingly, no crashes. So I thought I would be like super cool and find the first fully remote classifier bug, and sadly, this did not happen. But I still thought this was very interesting. I do think this attack surface still has a lot of potential, just because there's so much local zero-click native code. Another thing to know about these classifiers is none of them communicate with the network. They all classify your messages in a fully local context. So that's nice for privacy, but it means that there's no filtering. Anything that you send through will kind of directly touch these libraries, which makes them a great attack surface. And one thing I would say is I'm not as confident in this as I am other stuff. Sometimes I will look at an attack surface and be like, yeah, I didn't find anything, and I am reasonably sure that there is nothing there. And always, like next week, someone finds something in the wild, and I was totally wrong. But in this case, I am not even that confident. I think it's very possible that I didn't spend enough time to break through, and maybe if I spent 6 months on this, I might find something. Though there's other possibilities. This is also a very hot path. This is 5 billion users getting their messages through this, multiple messages every single day. So it is possible that there's not very many bugs here, because even if 0.01% of users are getting a crash, that is a lot of crashes, and it gets fixed fast. And the other thing I realized is that model is a big factor. So I've always liked this XKCD comic. This guy feels very helplessly alone after discovering someone in 2003 had the same issue on a forum that he did now. And this is kind of something I like to do when I do vulnerability research, which is, I will plug a few method names into Google and see if anyone has experienced crashes. And of course, my dream is that one day I will find a bug like this. One day I'll be reading that forum and I'll be like, ooh, that's still a good crash, and I will find a bug. This has never happened, but I'm gonna keep dreaming here. But what I do like about this is you can kind of learn about where crashes generally happened. And I noticed a few things here. There were people who experienced crashes who were complaining, when I got this message, my device crashed. But they were also all fixed and all seemed to be related to models. So I think that's kind of the real potential here, that maybe one day there's a bad model, or maybe with more time, someone could use the learning aspect, send the right stuff that will make the model learn for long enough that it gets into a bad state, and then they send the final message that leads to memory corruption. I think that's a possible research area that I didn't really look into. The other question I get about this is there a potential for higher level bugs? Could, I send a message that says, I love you, send me all your messages, and, get all of someone's messages back? And the answer to this, right now, is just no way. And that's because of how these classifiers work. So they're all functions that the messaging app calls, and they return specific things. And there is, for example, the sensitive content detector, which basically detects whether a message is upsetting. I'm assuming so they're not like, hey, do you want to take a selfie? And that just returns a Boolean. So what's the app going to do with a Boolean? There's detect language, which returns just the string with the language. There's suggest actions, and if there's anything that has logic bugs, I think this would be the one that has the most problems. But it still is, it's click required, and it returns an intent. And I looked at this, and there's only about 5 possible intents it can return. And they're all things like, visit a link, take a selfie, make a phone call, that sort of thing. So there might be, tiny injection possibilities, phone the wrong phone number or something like that. But this would require the click from the user. And also it's, kind of a minor subset of functionality. There is annotate, which just returns the text style. That's the thing that makes the links blue. And then there's push audio, which takes audio in and returns a string that is that audio transcribed. So, these things do not have unrestricted access to the system or anything like that. They get data, they give data back, and it's kind of a limited amount of data that is used by the app for specific things. So I don't think there's potential for kind of the big logic bug yet. But who knows what the future will look like. So overall, I think this is an interesting emerging area. I think this is also going to change a very large amount in the next couple of years. So I think more research is needed here. But I think it's pretty interesting and a lot of potential. So now that I had looked at all the shiny things, and spent a couple of months looking at the coolest part of the app, I got to turn this car around and actually determine and prioritize the attack surface and, maybe actually find some bugs. So this brought me back to the usual suspects. These are the 3 things that I find almost all my bugs and messaging applications in. And these are serialization, logic bugs, and media. So let's talk about serialization. Serialization, at least to me, is kind of how you get the bytes on the wire to the messaging class that is used by the app. And how this is supposed to work in RCS is that this is supposed to be in SIP. So you send SIP messages back and forth, and then the message is actually a multi-part MIME, like an email with attachments, and that is your message. And this is just lies. This is just not true. The specification says this, and the code is in the RCS app, and I was never able to hit it. Not true. The way this actually works, at least for Google-to-Google messages, is that this is all protobuf. So the message gets turned into a protobuf, it gets sent to Google server, and then on the other side, it is sent back down. So for me, this pretty much ruled out serialization bugs because I wasn't going to find a bug in protobuf. It's a very mature library. And I feel like there's probably 1 person out here who's like, well, I spent 6 months and I found a bug in protobuf. And it's not that any bug is code free, but I just felt that the amount of time it would take me to find one compared to the other possibilities in this app meant that this wasn't the most promising area. So next up was logic bugs. And that kind of means, now this message has been deserialized, what if the app kind of does something wrong with it that's not memory corruption? And there's sort of 2 main areas of this I see. There is directory traversal, and there's SQL injection. And, directory traversal, I feel like you're all getting out your phones being like, oh, is the year in fact 2025? And it is, and you still see these in messaging apps. And Yeah, it's very common, and it's because these clients handle just so many files. There's messages, there's photos, there's even stuff like if you scroll in a messaging app, that scroll is pre-prepared in a database so that you can scroll really fast and the screen doesn't stutter. So there's so many like little things where they will save a file, just for now so that everything runs fast. And this means like there's so many weird paths where there can be directory traversal. So this does happen. And then the next question is like, why does that matter? And these can be challenging to figure out what to do with because it's very rare to find a directory traversal in a messaging app where you can actually overwrite a file. Usually they have some redundancy against that because they don't want the messaging app to like accidentally clobber files that are being used. So they'll often put like ~1 after it if it is writing a file with the same name. So the best way to alter this is there's the DB journal or WAL backups for SQLite databases, and those, they're usually not there, but if you write them and then you kill the app and then start it up again, it will try and restore it from the DB journal, and that can allow you to change the database. And then after this, there's kind of two different attack paths. Path one would be that you hit a bug in SQLite. And I would say every so often I find a bug like this where you're loading the journal or you're loading the WAL file and there's memory corruption in SQLite. That is one potential. I think another one, which is a bit more promising these days, is to alter the database to access other attack surfaces. So maybe there is a static image somewhere and you can change that image to something else, or there's the ringtone and then you can make a different ringtone play, that sort of thing. And that's kind of the potential of this type of bug. So on the flip side, these are easy to find. You can decompile with APK tool and look for java.io.file, or you can run strace, and both of these will tell you pretty fast if a file is being written. So this is the flip side of this type of bug, which is that they have a short bug lifetime. Typically, bugs like this are found and reported really fast. So when I looked for this, I didn't find any bugs like this, but several bug bounty participants for this app did. So, maybe if I hadn't spent like 2 months looking at classifiers, I would have found these first. But they did get found fast and reported. But this is the area. It's also kind of what I described as high churn. This code changes fast. So I think it's likely that kind of every messaging client will continue to have these types of short-lived bugs in the future. The other potential is SQL injection. I was kind of hoping, that there might be one SQL query where they take, the incoming user's name or the contents of the message and don't sanitize it correctly in SQL, and then this would be a SQL injection possibility. And once again, then the path would be SQLite bug or releasing new attack surface. So I used Frida once again to look at queries related to incoming messages. You can do this by tracing SQLite.exec or native execute. There's kind of pros and cons to both of these with regards to reading the parameters. But with that, I was able to then send myself a bunch of different messages and see what the SQL queries were. And I also reviewed the Smalley for suspicious calls. And I found that they'd actually kind of found a way to mitigate this that was more effective than I expected, which is that when you're thinking about SQL injection in a messaging app, you really want to write. If you're thinking about a web server, it's okay if you read, you're gonna find out stuff that you didn't know. But when you're on a messaging app, if you can dump tables and you're sending a message completely blind, it totally doesn't matter. So the only relevant bugs here are ones where you can write SQL. And in the Android API, you can get a readable database and you can get a writable database. And it turned out that Google Messages basically did this correctly every time. They only ever got a writable database if they were planning on writing, which was quite a small subset of queries. So it turned out this attack surface was very small because they decided to do this, and I didn't find any bugs. So, that's not something I would have recommended up front if I was thinking about this problem, but it turns out it really stopped me. So yeah, no bugs here. This is another high code churn environment. This code is changing constantly. So I think in all the clients, it's pretty typical that these types of bugs, are introduced quickly and then go away quickly as well. So this brought me back to kind of my old faithful media. This is, one of the best places to find bugs in messaging apps. And while I was so taken with all those classifier libraries, like half of the libraries in this messaging app are also media. And that's pretty typical too. And usually they don't load this library. Usually what happens is they'll use the Android media handling subsystem, and then this is just the local native libraries are just a backup. So I looked at how Google Messages handled these. And I think an interesting distinction is that there is programmatic decoding, and there's what I describe as visual decoding classes. So visual decoding classes are things where they're in Java or they're in Kotlin, and you use the class to directly display an image or a video or to play an audio. And these are not especially promising for zero-click bugs, and that's because most of the time you're going to have the lock screen up and they're not displaying anything, so they'll always be a one-click attack surface. There's one exception in Google Messages, which is even if your device is locked, it will show a video thumbnail. So that's a tiny bit of attack surface where they'll spawn that image decoding screen and decode that one image. But one thing, and this is kind of good design for reducing attack surface, in RCS, it will never actually locally thumbnail a video. If you want your video to be thumbnailed, you have to send the thumbnail with it, and then it will just display that thumbnail. So that gets rid of, there used to be a good attack surface in Android where if you sent a video, it would try to thumbnail it before the user clicked, and there were lots of bugs there, but RCS doesn't have this anymore. But so I looked for situations that weren't these visual classes where it was actually programmatically doing this decoding with media codec lists and actually getting the buffer output from the decoding. And there was basically only one situation where they did this, which was transcription, which is still better than nothing. It never used to do this. So this also violates the spec. Back to me complaining about specs. The spec says it is only supposed to do this with AMR files, but this is not how this works. Transcription actually makes all audio a zero-click attack surface on Android now. The entire file is decoded, which is actually kind of rare for a zero-click attack surface. A lot of these, it'll be like it decodes part of the video, but this, it will beginning to end decode the entire file. It'll also remove audio from the container if it's in one, so this will also parse, MP4 and 3GP and all the other supported container formats. So that's a nice little attack surface. But on the flip side, Android audio codecs are also fairly mature and well-tested, so I thought this wouldn't be promising. But then I looked into how OEMs do this, and it turns out that OEMs can actually add their own codecs, and they do add their own codecs. And they'll automatically become available through this media codec list API, which actually surprised me. So this kind of means that every app will be using this, even if the developers didn't intend. So if I opened up like YouTube on a Samsung phone, it would use the Samsung codecs, even though obviously YouTube didn't intend to use them. So it's actually really integrated into the system. So I looked at a few devices, but these, Samsung was definitely the most interesting. And I wrote a little app that just dumps all the codecs supported by media codec list. And just, wow, this was like not what I was expecting. There's just all sorts of problems with this. One thing to know is that these codecs are actually in precedence order. So this is the order in which they will be used by the system. You'll notice for this device it is also alphabetical order, which means that the Samsung codecs are used first. So even for something like AMR, which there's an AOSP decoder that's pretty well fuzzed, it doesn't use that one first. It uses this Samsung implementation. There's also a lot of really odd codecs. There is Monkey's Audio, which is from like the year 2000. There is EVRC, which is the thing that decodes the audio in CDMA. There is QSELP, which is like an old audio video sharing format for SMS. So, yeah, lots of attack surface here that I wasn't expecting. So I was like, well, I should try fuzzing these. And I got what I'm going to call mixed results, which is that I thought I could just load one of these codecs into, use it as a library, write a C stub, and I'd be able to fuzz it. And this did not work. These codecs were way too bad. Believe it or not, if I did that, I just got like nonstop crashes, and then I would try them on the system, and they wouldn't crash at all. And this turned out to be because of how audio decoding works. So on all Android devices, it starts off in codec 2, and then it'll load the extractor. And the extractor is kind of like an audio and video format detector. So each extractor will be run in turn in the precedence order, and will come up with a score of how likely it is that file type. And once it finds something that's like over 50%, I forget what the exact threshold is, it'll decide that's the right file type. And then the extractor also has a read function, and then this codec 2 will start using the extractor to read from the file and get kind of the long pages of content that needs to be decoded. And then this codec 2 will pass it to the actual decoder. And I found kind of for my fuzzer to work, I actually had to recreate this chain, load in the extractor, detect the file, and then replicate the codec 2 functionality and make the stub run the whole chain. And this actually worked. This led to very reproducible crashes. And this is how I got around the poor codec quality. So unfortunately for this, I also lacked code or even x86, so I fuzzed on Jackalope with Android. And I'm going to put the link here. I suggest you take a photo, because Jackalope just changed my fuzzing life. I want to make sure that everyone knows about it. It was written by a member of Project Zero, Yvonne Fratrick, and it's a fuzzing tool that you can use basically with binaries where you don't have any code, and it adds coverage. And it's really nice. It's one command on the command line, super easy to use, and it will fuzz and do coverage-guided fuzzing and output your bugs. So super good. It really helped with fuzzing this. But what I found is on Android, it was a little bit slow. And I also didn't want to just fuzz on a device. So I ended up setting up some Linux ARM VMs. And then, I couldn't get my Android binaries to run on it. Then it's funny, someone on Project Zero was like, hey, have you just tried copy every single file off your Android device and just chroot in there and then run it? And this totally worked. So I was able to run my stubs on these VMs. And then I made a change to Jackalope so that, so Android doesn't have shared memory, but Linux does. So I mapped in the shared memory from Linux and then changed Jackalope so it could use it. So this made fuzzing super fast so that I could use shared memory to share test cases and basically fuzz back and forth very fast. So this was nice, and this is still ongoing. I confess I spent so much time on classifiers, I did not get all my bugs filed in time, but at least started this, and I have found one bug so far, which was in Monkey's audio. And this was kind of funny because I kept, getting all these crashes where Monkey's audio, the decoder, was writing outside of the output buffer. And I was like, oh, geez, I must just have got this wrong. Let's see how Samsung calculates the size of the output buffer and make sure that I'm doing it the same way. And then I discovered that they were just always allocating 20,000 bytes, which was the problem. So this turned out to be a super nice bug. It is controlled write size. It is controlled write output. It is a DMA buffer, but there is some fairly interesting stuff after this specific buffer. So I think this is probably an exploitable bug. And it's fully remote if you send this audio file, and it's transcribed. So yay, I found a bug. And this was fixed in December 2024, and I was actually a little surprised. They just hard-coded the codec so that now it doesn't write more than 20,000 bytes, which is not ideal, but hey, the bug's not there anymore. So this is where I am in this research right now. So what did I learn? Well, I still think that classifiers are an interesting new attack surface, and it's rapidly evolving, and I think that this is going to get a bigger and bigger attack surface over time. Because, right now, it's going in and just transcribing your audio files. But I feel like one day, AI is going to analyze your videos and tell you what's inside of them. One day, it's going to analyze your image files. And I think as this happens, it's going to kind of change the context of file decoding. And I think it's likely that a lot of these codecs are going to get back into the remote attack surface again, as these features are so new and so exciting that they end up getting put into messengers. The other thing I would say I learned is maybe everything old is new again. That even though there's this new attack surface, it does seem to always be the same things that lead to problems in messaging clients. And I think this can be a lesson for defenders that obviously you need to be concerned about everything, but it does seem to be media, serialization, and logic bugs that just hit messaging clients again and again and again. Finally, avoid the call of the cool. And I hate to stand up here, beginning this new conference, and be like, don't do cool things. But, and please, do cool things. It's very important to do cool things. But also, if I could go back in time, I would have probably spent, only 1 month on classifiers and spent a lot more time going over the more usual sources of vulnerabilities in messaging clients. And what I do think I really learned here is that there will always be new challenges and new opportunities in this space. The bug density of the software and messaging apps is going down, in my opinion. I really think this. I spend more hours these days trying to find bugs in software than I ever did before. And I think this is because of kind of new defensive technologies, because of consistent fuzzing, because of code review, and just because of people generally understanding more of what causes these bugs to show up in software. But on the flip side, there are just all these new features, and messaging apps always just get more and more and more. And some of these are really cool. I really like not having to listen to boring audio messages from my dentist. Transcription's awesome, but it also creates new risks. So that's something we need to be careful about. But what I will say is that I am absolutely amazed by the amount of innovation that has happened in the past few years, both offensive and defensive, and just in general. I mean, if you said, Natalie, in 2 years, your phone's going to tell you when you want to take a selfie, I just, would not have believed it. The landscape is moving to places we've never seen. So as we kick off this brand new conference, I'm excited to see this innovation. I'm excited to see what everyone has to share. Thanks so much.
Now I'm on. There we go. So before we let you go and ask some questions from the audience, I do want to thank you to be as our first keynote ever and give you a little trophy there. So I appreciate you very much for being here, Natalie. Super excited for that. I really do enjoy it. I think my favorite talks are the ones where you see both the successes and the failures in the process. So that was awesome. Let's go ahead and open up to the audience. I'm going to go ahead and run around with the mic. If there's any questions, we'll come out and you can ask them. We got some time.
Thank you so much, Natalie, for your talk. The first question I have is, what do you think about concurrency issues and race conditions within messaging apps?
I mean, I'm sure they're there. I'd be concerned about how hard they would be to exploit in that type of condition, just because in a browser or something, you can execute JavaScript and it's really easy, to do things, in a very controlled way with specific timing. But it's a lot harder to do that when you're a messaging app and the only control you have is sending messages. So, never say never, but I think there would be real challenges with exploitation.
Thank you so much. And has there been any instances where, following the call of the cool has helped you rather than sort of hurt you?
Oh, that is a good question. I think there's a bit of both. Like I would say, for example, that is what got me doing this in the first place. Back when there was like very few public reports of fully remote messages, me being like, oh, I might find one anyway, and looking at it. So it can definitely help, but yeah, I think it's also important to be aware of what's likely to find bugs. It is both a blessing and a curse.
Thank you so much.
Is it on? Make sure the switch is on.
Thank you very much, Jordan. Hi there, Natalie. I just wanted to ask, bringing shared memory into the fuzzing process, do you notice any false positives?
Not caused by that.
What were the main causes of false positives?
They were basically, so I guess two things. One was memory pressure. So sometimes there would be memory pressure that would make the codec behave differently. And they were kind of, memory pressure events that would be very hard to replicate in kind of the fully remote context. But most of my false positives were kind of due to my environment not adequately representing what was happening on the device. And I kind of, went through various iterations, removing the problems that were, causing false positives the worst.
Hi, I'm Matt Nelson from Red Lattice. This has been a great opportunity for me. I'm a customer service rep with the company, and you said something about not being, be worried about the cool. I did an internship with Google iCloud, and I wondered, hey, why did Google iCloud hire me? And I found out, I think what you're talking about is this kind of stovepipe that kind of happens in this community as well as when I was in the DoD, in which, where they hired me to say, hey, come help us manage that. What I've found on the front face for DoD is that, translating what they hear out in the news and then what you're talking about, these new vulnerabilities and messaging and all that. It's like how, I don't know how many customer service rep or if it's just engineers that are in here, but it's like, translating that to the folks that we serve. How do you recommend everyone in this room get better at translating these concepts to the people that we're trying to support?
Yeah, that's a good question. And I can kind of tell you just more of, in where I am, I find this is most challenging trying to translate these concepts to developers because, I can be like, OMG, I love this vuln, but getting it down to something that's understandable can be really tough. And I guess one thing is this can work for you, because I found, sometimes I will go give talks to groups of developers, and there's always, one person who's like, wow, that's so amazing, I love it. And, often that can be a person you can encourage to, get more interested in security and maybe promote security in this environment. But I think also, making people aware, sometimes showing people what attackers can do can really help them too. But also making sure that you have concrete recommendations, things are understandable, and often I'll try to stick to only a few things for developers. And for me, it might be a losing battle. Attack surface reduction is a super big thing. The less of this stuff that that is in, the less likely you are to find bugs in it. But of course, if you're putting in features that people love, that's a consideration too.
Any other questions? Peter, by you over there.
I'm curious about that monkey audio thing. It sounds like some obscure audio processing. What kind of message did you have to send? Were you able to weaponize it? What kind of message did you have to send to exercise the monkey audio?
So it turns out, so it's just in the main codec subsystem. So I discovered so I could only find one monkey's audio sample on the internet, but if I took that one sample and gave it an AMR extension instead of an APE extension, it would just play on a Samsung device. And I discovered so this required like a little bit of hacking. If I sent an audio message and then I would just like swap out the file before I sent it on the sending device with this one and gave it the AMR extension, it would just send it and this would be transcribed. And if you send the crashing one, it would crash. So yeah, it turned out like not to be that hard. This obscure codec was basically used in any context where audio was decoded on this device.
That's a good question, Andrew. I like that. Anybody else? In the back, Peter.
Hi, Natalie. Thanks for the great talk. So what context is this audio decoding happening in? Is it in media server? It is in the untrusted app context? Like, where is it?
It's in media server.
And so what do you think about the exploitability of that then? If it's in media server, that's obviously a lot harder surface.
Yeah, so like I think there's potential there, and I think you're probably asking about two things. One is like how exploitable, and the other thing is breaking out. And I would say exploitability, I'm unsure of. In this particular case, there was like a fair bit of stuff afterwards. The other thing that's interesting about these decoders is that they also have a lot of inline pointers. So yeah, like this is one where I haven't tried yet, but I think I could probably work it out. And then the other question is how do you get out of the media service? And this is something that a couple people on my team have been working on, especially Jan Horn and Seth Jenkins, if you want to look further, like blog posts and conference talks. And there's a lot of issues in Android drivers that are reachable from that context. So that's kind of what I think the next step would be.
Thank you very much.